and I'd like to welcome you to this presentation by Professor Eric Mazur, Peer Instruction, Confessions of a Converted Lecturer. I'm especially glad to see Professor Mazur, who was battling New England weather and plane mechanical difficulties, but managed to sneak out of Boston, and we're very glad he was able to make it here today. It is a real treat for us to be hosting Professor Mazur. We at CRLT have used his work on peer learning for many years in workshops and when we consult with faculty who are interested in creating a more active and engaged classroom and in using a research-based approach to do so. Professor Mazur has become internationally recognized for his work in this area, and we are very pleased that he is able to be with us today. We're very pleased to have so many collaborating groups involved in making this visit possible, and they include the College of Engineering, the Learning Analytics Task Force, the LS&A Dean's Office, OVPR, and the Departments of Physics, Astronomy, Biophysics, Chemistry, Earth and Environmental Science, EEB, and MCDB. Quite a team effort here to bring Professor Mazur. And finally, I'd like to thank and introduce Steve Yalosov, who's a professor of materials science and engineering. Professor Yalosov shares a common research area with Professor Mazur, and he's also implemented many of Professor Mazur's ideas into his own teaching to great effect. He's been instrumental in helping to arrange for this visit, so I'd like to thank him and invite him to come up here to introduce Professor Mazur.
Thank you, Matt. And it is a real pleasure to have Eric come and visit us today. Eric came here in, I think, 1996, and I missed his lecture. But I didn't miss his message. And I started using clickers that very next year before clickers existed, because I think Eric was the first person to really initiate audience response systems in academia. I think before that, the only clickers were used, during the disco days of the '80s and bar trivia. But at any rate, I started using clickers way back then, and I was probably one of the first to use it on campus. I was probably also the first to reject it because it got in the way of my lecture. And it took me years to figure out what Eric was really saying. The problem wasn't the clickers. The problem was the lecture. Eric is the Balkanski Professor of Physics at Harvard University. He's the Area Dean of Applied Science at Harvard University. He has a huge research group. He is one of the pioneers of ultra-fast laser interaction with material, developing double-angle reflectometry and really probing the time evolution of the complex dielectric function right after an ultra-fast laser hits within 20 to 100 femtoseconds after it's over. He's also the discoverer of black silicon, black metals, other kinds of morphological changes which have spawned companies. He has a company making infrared detectors that's very successful. He started 2 education companies, one of which is Learning Catalytics, a company that went from inception to sale to Pearson in just 20 months. I use that product. It's fantastic, and you're going to hear more about that at the lunchtime slam talk. Eric is a wonderful person in the way he shares what he knows, and he has helped me tremendously through my journey of learning. And I'll never forget one day sitting at Photonics West outside on a sunny afternoon. I was proudly showing Eric my new tablet PC and saying, "Isn't this cool? I can actually capture my lecture, and I can give it to my students after it's over." And he looked at me and he said, "I would never use that." I go, "Why not?" He goes, "It's not a Mac." And then he said, "But it's a good idea. Why don't you just give the students that video and then take them to Starbucks and talk about what you really want them to learn?" And so I've gotten little insights from Eric over the years, and finally, when I met him last November, a year ago in November, he invited me to come over and see his class, AP 50, which is the culmination of 30 years of his ideas and putting something together that is just remarkable. And so I thank you, Eric, very, very much for all of your help. It's changed my life, and I hope it changes the lives of my students. So I'm very proud to have you speak to us, Eric Mazur.
Thank you, Steve, for that very kind introduction. Wow, there are a lot of you here. That makes me nervous. Now, could I turn this off? I give you this. I give you the microphone. I'd rather be confessing, you know, one-on-one than in front of so many of you. I guess I'll have to remind myself of the American proverb, the more you confess, the more books you will sell. Anyway, let me start with the very first confession. When I started teaching at Harvard, which I guess this fall will be 30 years, wow, I never asked myself the question, how am I going to teach? It was completely obvious to me what I was going to do in the classroom. I was going to do to my students what my professors had done to me, lecture. Now, you know, I think we all tend to do that. We tend to project our own experiences onto the world around us. And I naively thought that I had learned physics sitting in a room not very different from this one and listening to my teacher's lecture. And what happened was that very quickly this feeling of doing the right thing was actually reinforced. What are the metrics by which we evaluate teaching? I can think of two of them. One is the end of semester questionnaire. I had been asked as a beginning assistant professor in the physics department to teach the course that absolutely no one wanted to teach. Physics for pre-medical students. These were not students who wanted to learn physics. They already hated physics before they set foot in my classroom. You know, usually at the end of the semester, most of my colleagues, when they used to teach that course, would come close to committing suicide because the evaluations were not very pretty. But not so for me. I got a 4.5, 4.7 on a 5-point scale. So clearly, the students liked what I was doing. So that's one metric. The other metric was my students' performance on the examinations. Now, typically, when physics is taught to pre-meds, it's an algebra-based course. Not so in my class, full-blown calculus-based course. And I could give these students some exam problems that I wasn't quite sure I would do well on an exam, and, you know, under the pressure of an exam. But the students did quite well. So in short, they liked me as an instructor. They did well on what I considered difficult exams. Obviously, I was doing the right thing. In fact, very quickly, I started to believe that I was the world's best physics teacher. And that illusion, which as I said was a real illusion, went on for many, 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 many years. Even though, if I think back, there were negative signs all along. But you see, I'm a positive thinker, so if I get positive signs and negative signs, I ignore the negative ones and focus on the positive ones. Let me give you some examples. Each year, in spite of giving me high marks on my end of semester evaluation, some students would write in the comment section at the bottom, "Physics is boring," or "Physics sucks." I could never make any sense of that. I mean, what is more interesting than understanding how the world around us works, right? So it didn't make any sense to me. So I ignored them. And you know, the same thing happens when I go to a party and people ask me what I do for a living, and I tell them I'm a physicist. I get these worried looks. Physics? I had such a hard time with physics in high school or in college. Or my dentist, who recently told me, and you know, I couldn't even talk back because I had the thing in my mouth, said, you're a physicist. I got an A for physics in college, but I really didn't understand anything. It always creates this feeling of embarrassment, as if I should defend my discipline, and I could never make sense of it. But I think I now understand much better what the cause of the problem is. Okay, we'll get back to that in just a second. You all have a little clicker in your hands, and there's a danger in starting any talk on education with technology. Usually I brush the technology aside because ultimately, and I'll repeat this at the end of my talk, it is not, whoops, I think we need to turn the volume down a little bit. It is not the technology that matters. It's the pedagogy that matters. And you know, with clickers in particular, I see so many people adopt the clickers for technology's sake, expect better results, but they don't really think about the pedagogy, which I will emphasize in my talk today. And you know, then they don't get the results that they want. And in fact, the investment that is made in technology, I love technology. You'll find all the latest gadgets. We need to turn the volume down a little bit so we don't get feedback. You know, a lot of investments are made in technology. Each time there's a new technology that could be used in education that comes out, you know, people invest in it, and then a little later, you know, they're not happy. Why? Because most uses of technology in education are simply old wine into new bottles. Why would, for example, a lecture delivered by video on PowerPoint be better than one delivered without PowerPoint or video? I think the right uses of technology are those that afford a new mode of learning. And if you ask yourself, evaluating educational technology, whether most technologies do that, no. Smart boards. We don't need smart boards, we need smart students. You know, and so on. So this talk is not about technology, but because I want to give you a little exercise, I'm going to briefly show you the technology. So the clickers have no on-off button, they're always on. I'm going to ask you multiple choice questions. Later today, if you come to the workshop at lunch or the seminar at lunch, I'll tell you how you can get rid of multiple choice questions because there's a significant problem with multiple choice questions. But you'll click a button, 1, 2, 3, 4, 5, and so on. And if, let's say, you accidentally hit the wrong button, don't worry. You can click the right one, or what you think is the right one, and that one will replace your first vote. The only button I ask you not to press is the channel button on the bottom left. Because what happens then is you can change the channel. The little light will start flickering. If that happens, just wait and it'll stop flickering. But it allows you to change the transmission channel. We all want to be on 41 here. The reason is that if you have two classrooms nearby using clickers, you don't want the students in that classroom to vote in this one. All right? But we're all on 41. And if you press a button, then the display will show you the answer that has been received by my receiver. This is what I see. I have this tiny little window that floats in front. I see that 68 of you have been playing with their clickers. Very good. Why don't you just all press the button, and you see that this, there, very good. You'll see that this counter here increases. We're at 185 right now. Very good. At any point, let me make this display a little bit bigger. I can hit this, well, first what I can do is actually I can show the distribution. A lot of you like button 5. Why don't you all press button 1 now? Go ahead, press button 1. Very good, I love it when audiences follow my instruction. And you see that the distribution immediately changes, and if I hit the stop button, you can no longer change your vote. If you now press a button, you'll see a circle with a line in the little display. So that's all there is to it, which is important because you don't want to be fighting technology when you're in the classroom. That's all there is to the software on the instructor side, which I'm showing you here. Except for one more thing. What happens is that when I press this stop button, it takes a picture of the screen behind, and it stores that together with the data. So when I review my session file, if you want, tonight, I can see that I had this on the screen while we collected that distribution. So that means I don't have to program questions in, nothing. It's all done completely automatically. Okay, one more thing. Turn the clicker around for a moment, and you'll see that there is this barcode. You may think you're sitting here anonymously. Sorry. Each time you press a button, that barcode is sent over, and recorded together with the button you press. Of course, I don't know which barcode you have, so for all practical purposes, you're sitting here anonymously. But in a real class, you might be able to track individual students. Now, some instructors use that to assign points, either for participation in the lecture or for getting the answer right. I would argue very strongly against doing that. You give credit for getting the questions in class right, and students are going to do everything they can to get the question right, including Googling it and you name it. It no longer becomes an opportunity for formative assessment, as I will argue later on. You give points for participation, and yes, your students will participate, but only their bodies will be in the classroom, not their minds. Or you will have students who bring in 4 clickers for 4 different students, including their own. In fact, if you are on Twitter, I urge you to do a search for the words class and clicker together. It's hilarious. You'll get a real insight into how the students perceive the use of clickers in the classroom. And you'll see many students posting pictures for, where they're sitting in class with their own clicker and those for 3 or 4 of their classmates. That defeats the purpose. You don't want your students' bodies in the classroom. You want your students' minds in the classroom, and I'll show you how to do that. Okay, so let's start with a little exercise here, because this talk is about education, not about technology, so I want to put the focus back on education. And I want to start by having you reflect on your own education. So please take a little piece of paper. In fact, there's a nice little piece of paper on every seat, so you might want to use the back of that. And I'm going to ask you 2 questions. The first one is a very personal question, but don't worry, I'm not going to ask you to reveal your answer. It's purely for yourself. Here's the question. Think of something you are good at, something you do really, really well, something you're proud of. You know, when you're good at something, you know that other people respect you for it, you feel good about doing it. It could be, I don't know, it could be solving partial differential equations. It could be baking cakes. It could be interpreting medieval works of arts. It could be carpentry, whatever. Something that you know you do really, really well. And ideally, I want that something to be a skill or knowledge that has been important in your career. So unless you're a baker, baking cakes will probably not be in there, but you get the picture. And you're all successful individuals, so it shouldn't take you very long to write that down. So please write that down. And then once you've written it, turn the piece of paper over so nobody can see what you wrote down, because it's personal information, but I do want you to commit to it. You know, usually when I do this in an academic environment, it doesn't take very long for somebody to raise their hand and say, only one thing? Yes, just pick one. If you're good at many things, pick one. Okay, anybody need more time? You're in trouble if you need more time. Good, okay. So now you can hide this, but I had you commit to it because it's important for the next question. Because now I want you to think about the following question, which is much harder. How did you become good at whatever it is that you wrote down? Where did you develop that knowledge or that skill? What were the circumstances that led you to become good at whatever it is that you wrote down? Now I can see it right away. You know, the first one, when I asked the question, everybody started writing down. Here, everybody's staring in space. It's a much harder question. Why? Because when we're good at something, we tend to enjoy it. When we enjoy it, we take ownership of the learning. We learn, you know, without even being aware of the learning. So dig back in your past, in the memories of your past, and try to write down in a few words. It doesn't have to be an elaborate answer, you know, 5, 6, 7, 10 maximum words. What were the circumstances that led you to become good at whatever it is that you wrote down? Go ahead. Incidentally, I've done this little exercise. I'm not trying to distract you here, but I know that some people have already written down things, so I want to have something for them, I have done this little exercise all over the world. China, all over Asia actually, all over Latin America, the US, Europe, Australia, Africa, Middle East, very different cultures. And there's something really interesting because I've collected the answers to the second question. And there's no difference. Yes, there are cultural differences between the people in Chile and the people in China, or the people in Egypt and in the Netherlands. But if you collect the answers to this question, you find that the response you get is more or less the same, which is perhaps not that strange because we're all human beings. Our brains are wired to learn in the same manner. Now, I've never done it in Michigan, so I don't know. Let's see if you're special. Does anybody need more time? Did you all write down something? Okay. So I've collected the actual responses, and I've constructed a multiple choice question out of that. And here are the predominant categories that are reported by people. I became good at it by trial and error, by trying it and making mistakes, correcting my mistakes, and continuing. I became good at it by listening to lectures. I mean, the word listening is not on there, right? But I want to be sure, as we all know, the teachers among us, teaching something and giving lectures is a very different activity from listening to lectures. So I don't want to be misunderstood as giving lectures. I became good at it by practicing. I became good at it through apprenticeship, you know, by tagging along with somebody who's really, really good at it and then learning from that person. And then there's a mishmash of other categories like friends and family and so on. Pick the category that is the closest to what you wrote down. And then let's see if you here are the outlier that I've missed all these years. I did get an IRB approval for this study, but I'm just kidding. I should write a paper about it. Okay, so a few more seconds. We got 205 votes here. I'm going to cut you off right now. And no, I get exactly the same response. And in fact, you're right smack in the middle, typically between 50 and 70%. And with 60%, you're right there in the middle of people report they learned this by practicing. So you can relax. You're no different. You're not an outlier. You're the same as everyone else. But that's not why I'm doing this little exercise, because there's something else really interesting about that distribution there on the screen behind me. What is it? B2, the lectures. Only a few poor souls, pity on you, chose the lectures. So, you know, how do we teach though? This is how we teach. This is actually a very old picture of me teaching my pre-med physics class many, many years ago. This picture is a very old picture. It's taken BC, before computers. You see I'm using an overhead projector there. So right off the bat, we see something rather interesting. We teach by lecturing in spaces very much like this one here. We learn by practicing. Something that has been important, you told me it was important, or I asked you, it was important in your career. You did not learn that in a lecture. So here's what I'd like to do today. I'd like to talk a little bit more about education. What is education exactly? What do we mean when we use the word education? Think about it. If I were to ask you to write down on a little piece of paper a concise definition of the word education, I think many of you would be struggling. It's very hard to articulate. We know what we mean, but to actually express it is not that clear. Now, we're educators, so we ought to know what we mean. Then I'll talk about peer instruction, which is an approach to teaching that I developed once I discovered that my students weren't learning anything at all in my lectures. And given that we're in an academic environment, I thought I would actually end by giving you a test. So, you better pay attention until the end, because that's when we'll start having real fun, or at least I will have real fun. So let's start by talking about education. What is it that happens actually in a lecture? Let's go back to that picture of me teaching my pre-med physics class there, standing in front. It's a grainy picture, but as I told you, it's a real old picture. I want you to describe the process that is happening on the screen behind me. And ideally, I want you to use a verb. But there are two verbs I do not want to hear: teaching and learning. So you have to find other verbs. So go ahead, blurt it out. Watching. Transfer of knowledge. Dosing. Oh, exposing. Yes? Modeling. Come on, let's get it going here. Wait, did I hear somebody say sleeping? This time I didn't miss that, but well, first let me give you a quote which I find very interesting, because it turns out that sleeping is actually very close to the truth. I'll show you some really exciting data from MIT towards the end of my talk, but now I just want to remind you of a quote from Albert Camus, who once said, "Some people talk in their sleep. Lecturers talk while other people are sleeping." But these are my students. They're not sleeping. They're awake. Now, a lot of verbs we heard pertained either to me or to the students: exposing, modeling, watching, sleeping, writing, whatever. There was just one person who mentioned something that is about the process as a whole: transfer of knowledge. But let's face it, can you actually transfer knowledge? I don't think I can transfer knowledge. Knowledge is something that needs to be constructed in the brain of the student. It needs something that needs to be developed. You cannot just transfer knowledge. But I like the transfer part, for sure. So can we modify that statement a little bit? Transfer of information. Exactly. That is actually the process that is happening both here in this classroom now, or this room, and my classroom there. And you know what? My students had actually rubbed that in my face. And I had ignored it very early in my career. You see, when I was assigned that course, I didn't ask myself, how am I going to teach? What was the question you think did come up in my mind? What exactly, or more precisely, what book? So I went to a colleague who had taught this course before, and he said, oh, in this course we've used Halliday and Resnick, a book that is still being used 30 years later, believe it or not. And I was told that in the US, I was educated in Europe, and in Europe, for introductory science courses, you never get it into your mind to buy the textbook. Why buy the textbook if the faculty member is presenting the content of the book to you? But anyway, I was told that in the US, every student bought a copy of the textbook. So I went to the bookstore and I said, be sure that by September 15th, you have 150 copies of Halliday and Resnick in stock. And as I walked back to my office, I thought, wait a minute. If the students have the book and I have the same book, then what do I do in the classroom? Oh, so I stopped at my colleague's office again, knocked on his door, and I asked him that question. And he said, oh, don't worry. There are lots of different physics textbooks. And he showed me a shelf full of different books. And I started looking, and very quickly, I identified the perfect book. It was perfect for two reasons. One, it had a different approach from Halliday and Resnick, so at least I was not just regurgitating the book that the students had bought. But that was not the important reason. The important reason was the book was out of print. Anyway, so for every class, for every lecture, I prepared lecture notes to lecture from. And then in class, I would either put them on the overhead projector, as you see on this picture, or I would write it on the board behind me. And at the end of class, because my notes were different from the textbook, I decided to hand out copies of my notes to the students. So as they walked out at the end of class, they could pick up, this was before the internet, they could pick up a copy of those lecture notes. Now, why do you think that I hand them out at the end of class and not at the beginning of class? So they would pay attention and listen to me. Right, but if you stop to think about it, isn't that already admitting that there's a problem? Why force them to get the information out of my mouth if they could get it from my notes? That never came up in my mind. But what did happen was the following. At the end of the semester, in spite of my high evaluation, about half a dozen students wrote in the comment section of their evaluation, Professor Mazur lectures straight from his lecture notes. Hello? I mean, what was I supposed to do? Develop another set of lecture notes to lecture from that was different from the lecture notes I handed out? I mean, I was livid. These ungrateful students. But you know, the students had a point. I was lecturing from my lecture notes, and if they had looked at the book, they would have seen that the information in the book wasn't that different from that in my lecture notes. Now, given that this model that I'm just presenting here is used all around the globe, and trust me, I travel and visit many universities all over the globe, and I make a habit of stopping in different classes on campuses, and whether you're in South Africa or in Egypt or in China or in Korea, you see the same scene. So that leads to the question, is that what education is? Is education simply the transfer of information? I don't have a slide, but you know, I want to engage you a little bit here. So let's do a quick poll. If you believe that education is just the transfer of information, press 1. If you think information is more than just the transfer of information, press 2. So go ahead. And let's see where we stand. I'll cut it off when we get to 210 or so. Oh, we're already there. Good. Okay, so let's see. Oh, look at that, C and H. I think somebody held his clicker upside down. I don't know, we'll ignore those, but I'm happy to see that an overwhelming majority chose 2. Those who chose yes are probably the ones who learned from lectures in the first place, who answered that other question. Let me first turn to the few people who chose 1. You're about to lose your job. Because let's be very pragmatic. Let's imagine for a moment that education is just the transfer of information. If that's the case, what would be the pragmatic thing to do? Lecture notes, a book, but look, we're in the 21st century here. Teach students to use the Wikipedia, or just record the best possible, you know, physics lecture in English and Chinese and Spanish, and do the same thing for the other disciplines and put it on the internet. In fact, it's happening right now. What would you lose by doing that? What would you lose by abandoning all classes and putting online, either using books or using video? What would you lose? Interaction? You know, I'm working really, really hard here on interacting with you, but in a standard class, as I told you, I make a habit of observing, both on my own campus and other campuses' classes, and you know, I see these brilliant lecturers pacing in front of the class, and then after a few minutes they stop and they said, does anybody have a question? Anybody? And you know how students are, they look down, they don't want to make eye contact. And then, you know, if the instructor waits long enough, it's always the same person in the front row who lectures. It's very hard to interact. Why? In part because of the architecture. Who invented this architecture? The Greek, the ancient Greek. For what purpose? Performance, theater, music, theater in particular, right? And they did it with 2 purposes. One, so that everybody could see the performers and everybody could hear the performers. And when you sit down, in fact, when you came in here and sat down, you immediately took on a passive role. You're sitting down expecting to observe, not to interact. So I think you'd lose very little interaction. In a class of 300 students, you may lose interaction with one student. So that's not something you really lose. And of course, you'd lose your job too. What would you gain by putting it online? Or giving a book? Or giving the lecture notes, because they're all other modes of transfer of information. You'd gain a lot because you create an opportunity to think. When you're sitting in a lecture, there's no time to think. Have you ever had a student in your classes raise her hand and say, "Professor, could you please be quiet for 5 minutes? I need to think." It's never happened to me. But you know, if you read a book and you need to think, you can stop reading and think. Or if you're watching a video, a lecture on a video, you can hit the pause button and think. In a lecture, you can't do it because your mind starts wandering and our brains are not wired for multitasking. So you either think or you listen. You cannot think and listen at the same time. So in a lecture, you're forced to maybe write it down and tell yourself, "I'll think about it later," which often does not happen. So you'd actually create an opportunity to think. There's another benefit. Have you ever had a student raise his hand and say, "Professor, could you please repeat the last 15 minutes? I need to hear it again." Never happened to me. In a book, you just reread. Online, you can just scrub back and play again. So I think if education is just a transfer of information, we are in trouble. But luckily, 93% of you agree with me that there is more to education than just the transfer of information. So now let me pick on the 93% here. What is it? You said no. So what more is education than just, because I think we all agree the transfer of information is essential, right? No transfer of information, no education. But what more is necessary? Inspiring. Practice, very good. That's why I started with that little exercise. You need to do something. As a learner, it's not good enough just to open your skull, put the information in, close your skull. Even though so much of education is simply instructors transferring information to students. Then you wait 1 or 2 months. You isolate the students from each other and from any source of information, a situation they will never encounter in their professional lives, and you have them regurgitate exactly the same information back. I was educated in Europe, and you know, we tend to pride ourselves in good high school education in Northern Europe. But you know, if I think back of it, it was all also an illusion. Because I grew up in the Netherlands, the focus was on Dutch history. And I remember, you know, at some point I learned about how the Dutch had defeated the British in the River Thames just outside London in I forgot. Maybe somebody can Google it. I forgot what it was, 1660 something. Battle of Hastings. And you know, on the exam, in what year did the Dutch defeat the British in the River Thames? Well, I've forgotten. I must have done reasonably well in high school, but I forgot. Did I learn something of value by memorizing that date? I have no clue why the Dutch were even fighting the British and how they managed to beat them all the way up the River Thames. So I think this transfer of information, this mutual transferring back and forth of information is sort of a, you know, house of cards. Anyway, so the important part is not the transfer of information. The important part is making sense of that information. Assimilating. Piaget would have called it accommodating. I'll use it, assimilating that information. Building the mental models that allow you to transfer what you've learned into a new context. Not that long ago, I was giving a talk. I'm getting sidetracked in anecdotes here, but I can't resist telling you this. I was at a well-known university in Connecticut. I won't name any names. And I was giving a talk in the physics department, and after my talk, one of the faculty members came up to me and he said, I had something really peculiar happen in my classroom this year. And he said, look, he had taught physics to engineering students, and he wanted to make physics relevant to the students. So he put it into a real world context. And the context that he used was baseball. I mean, there's a lot of physics in baseball, right? Trajectories of balls, collisions between balls and bats, runners running. So in class, he would use examples from baseball. On the homework, he would put baseball problems. On the midterm examinations, he'd put baseball problems. At the end of the term, he was preparing the final exam. And he realized he had run out of baseball problems. So he put some football problems on the exam. Professor, complained to students, we have never done any football problems. You're laughing about it, but you should really be crying about it. Because if you're unable to transfer what you've learned from one context to another, you have not really learned, right? Therefore, this regurgitating back of information is not sufficient. It took a long time before and I wish I could show you the data, but I don't have time because of the test that I'm going to give you at the end. But if you're interested in the data, on my website you can find all of the data, and there's a version of my confessions talk, which is a little bit older, which has the data on YouTube. But what I found out is that my students weren't really learning. What happened was that in the early 90s, I ran across a test that tests students' conceptual understanding. Now that I mentioned tests, some people are leaving. I guess they're getting worried. That tests students' conceptual understanding of the concept of force by simply asking word-based questions. I didn't believe, and the person who had collected data on this test in California, Arizona, New Mexico, Colorado, showed that there's not much difference whether you ask the questions at the beginning of the term or the end. You get more or less the same answers back. I couldn't believe it. So I decided to give it to my students in an attempt to show that my students at Harvard were very different. Well, as soon as I gave this test to my students, I fell out of my ivory tower. Because within 5 minutes, one student raised her hand, and she asked me, Professor Mazur, how should I answer these questions? According to what you taught me, or according to the way I usually think about these things? I had no idea how to answer that question. And it was clear after they had answered this test that, the students in my class were not really learning. They were able to solve problems by rote, but they had not really internalized the physics. So it's not the transfer of information that is important, it's the assimilation of that information. And that led me to think about education as a sort of a two-step process. One, the transfer of information. No transfer of information, no education. I think we all agree on that. But there's a second step, which is making sense of that information. Ask yourself, where did that second step happen for you in your classes? Did it happen while you were sitting in the classroom, listening to your instructors? Where did these aha moments, oh, I get it. Where did that happen? Did that happen while you were listening to a lecture? Maybe occasionally, but I would argue that most of that happened outside of the class. So in the traditional approach to teaching, that first step takes place in class, and the perhaps much more important second step is left to the students on their own outside the class. So back in 1991, I decided I should really focus on that second step, not the first one. I should throw the more easy first step out of the classroom so that I can use the time in the classroom to help my students make sense of the material. I didn't think of this wonderful term, the flipped classroom, that came much, much later, but I called it inverting the sequence. So there's a lot of discussion about the first step. How do you transfer information out of the classroom? MOOCs, putting things on the internet, and so on. To me, that's not the interesting part of education. It's a trivial part. And I'm not a firm believer in transfer of information through video. I think there are many problems with that. So I don't even want to discuss that. If we assume that there are ways to transfer knowledge outside the classroom, this is the question I want to answer in the remainder of my time, what do we do in the classroom? So I'm going to talk only about that second step right now. And the answer to that question is actually nothing new. Teach by questioning. Who said that the first time, by the way? Socrates, 2,000 years ago, and here we're in the 21st century, still mostly teaching by telling rather than by questioning. It was a completely serendipitous discovery. You know, I gave that test to my students that I told you about a moment ago, where the student asked, how should I answer this question? And this was about 2/3 into the semester. And the questions only dealt with the material I'd covered in week 1 and week 2 of the semester. And not only was I horrified to find out my students did poorly, the students were horrified themselves too. I mean, they had midterms coming up on rotational dynamics and integrating volume integrals of complicated objects. And I mean, I don't want to scare you away, but they discovered that they didn't understand what I had discussed in week 1, Newton's laws, basically. So they were horrified, and they asked me for a session to go through every single question on that test. And there was one question that dealt with Newton's third law, where, you know, to me the question was completely trivial, so I made a sketch on the board, and you know, within 2 minutes I said, by Newton's third law, this force is equal to that force. To me, in my mind, there was nothing else to explain about it. So I turned around, and I could at once see from their faces that they were confused. So I said, is there a question? They were so confused they could not articulate a question. You know how it is, right, when you're really confused. So I thought, this is serious. So I turned around, I erased the board. I thought, okay, let me bring in some more mathematics. And, you know, in the next 8 minutes, I managed to produce the most brilliant explanation you could possibly imagine. At the end of 8 minutes, the entire board was covered with drawings and formulas. I mean, I was so proud. I brought in acceleration, forces, everything. I turned around, my coat jacket was covered in chalk dust, only to see that they looked even more confused. And they could still not articulate a question. I knew, however, that on that quiz, on that test, half of them had given the right answer. So in a moment of despair, I did something I'd never done before. I said, why don't you discuss it with each other? There were 250 students in the class. And something happened I had never seen before. The entire classroom erupted in chaos. They forgot about me in front of the class. I could have walked away. They would not have noticed. But the biggest miracle was that in just 2 minutes, they figured it out. I said, how can that be? I've tried for 10 minutes, I, the expert, to explain it unsuccessfully. And in 2 minutes, they just figure it out? But imagine 2 students sitting next to each other, John and Mary. Mary has the right answer because she understands it. John does not. On average, I won't say this always works, but on average, Mary is more likely to convince John than the other way around because she has the right reasoning. But that's not the important point. The important point is that Mary is more likely to convince John than Professor Mazur in front of the class. Why? Because she has only recently learned. She still knows what the difficulties are that a beginning learner has. She still knows what John is struggling with, whereas Professor Mazur learned it such a long time ago. To him, it is so clear that he can't even understand why somebody doesn't understand it. It's what my colleague Steven Pinker calls the curse of knowledge. Sort of an ironic argument, right? Because you think the more of an expert you are, the better qualified you are to teach. But think back of your own education. It's certainly true for me. I would often not bother asking my professor. I would just go to a friend and say, hey, did you understand? Because I know I'd get an answer right over my head. Hey, I'd go to a friend and say, hey, do you understand what Professor such and such said? So that's one benefit. The other one is that students can address each other's individual difficulties instead of, you know, sort of the cookie cutter approach from the instructor. You personalize the instruction in parallel, massively in parallel. So I'll step into the classroom, I talk a few minutes, I ask a question, and then I give students time to think. It's completely silent, no talking. And after they think, I poll them. We'll talk during the day about several ways of polling. We have clickers here, but you know, the clickers are really non-essential. You can do it without clickers. And then I asked them to turn to their neighbor, to find a neighbor who has a different answer. You know, students are very happy to talk to their neighbor if they have the same answer. You actually have to tell them, find somebody who has a different answer. So if you turn to your left and that person has the same answer, turn to your right. If that person also has the same answer, talk to the person behind you or in front of you, or get up and walk around. You've got to find somebody who has a different answer in order to try out your reasoning. Complete chaos. Then I polled them again. And usually, if this first answer has, let's say, between 30 and 70% correct answers, this is for questions that have correct answers, and you can adopt the method in case you teach a course where there are not questions that have necessary correct answers. But if you have between 30 and 70% correct answers, the percentage of the second poll will usually jump up tremendously. And then we wrap up by explaining. Either I can explain it, or I can ask for one of the students in the classroom to wrap up the course. And then that repeats, and the cycle basically repeats until class time is over. And of course, the important part is this discussion. That's where the aha moments occur. You'll actually see students go, oh, I get it now. And that's probably one of the most rewarding things of teaching this way. Let me show you a little video clip of how this works in practice. So we have a rectangular loop. Don't worry about the question. It won't be on the test, okay? Field in the direction indicated. So I read the question with them. So the question is, what are the magnetic forces on the 4 different sides of this loop? So take a minute to think about this and then enter your answers. You can move it down a little bit. Yeah. Please enter your answers. So they vote. We have a I see the distribution. I do not show the distribution to them. Here. So turn to your neighbor and see if you can convince one another of the correct choice.
Right. It goes out of the page and the top goes in, so they cancel each other out. There is a torque. There is a torque.
How do you know that?
I said, what did you say? But how can it be a torque? Oh, so it was
See the aha moment there? Ah.
Initially, we had sort of an even split. And now we have an absolutely overwhelming majority for choice number 2.
And this is not unusual to see it go from, 50-50 to an overwhelming majority for the correct answer. Very seldom does it go in the other direction. They do see that second distribution, not the first one. So what's going on here? One is that it's active, not passive. It is impossible to sleep through my classes because every few minutes your neighbor will start talking to you. Believe it or not, some students actually rather sleep than being awake. Secondly, there's a two-way flow of information. It's not just information from me to the students, there's information coming back. If they don't get something, I see it then and there. But most importantly, there's continuous information on the learning going back to the students. If you're in this class and you're among the few percent who gets it wrong on the second try, you've gotten feedback. Feedback in a completely non-threatening way because it doesn't factor into your grade. It's okay, but at least you know that you have to look at this in more detail. It's continuous formative assessment, which is so important, right? We focus so much on summative assessment at the end of the semester, but the feedback part of the assessment is much more important than the ranking part of the assessment. Do you want to try it? Yeah? A little bit more enthusiasm. Okay, good. I hope you all read those 2 little paragraphs that were circulated by email on thermal expansion, because that's what I'm gonna test you on. No? Did we miss? I'm just kidding. But you know what that means? That means that I will have to lecture you on thermal expansion, because I can't just, it would be unfair to ask you a question without you knowing about it. But I'm actually very happy about that, because the one thing I miss about peer instruction is I don't get to lecture in my class anymore. So thank you for giving me that opportunity here. So thermal expansion, which has to do with the fact that materials, solids, expand, and it's particularly pronounced for metals, that's why I said metals accidentally, but all solids do that, expand when they get hotter, bigger in volume. And then when they get colder, they shrink again. True for concrete, true for metals. I mean, any hard solid will do exactly the same. And the reason for that is that solids are made out of atoms, some regularly arranged like the ones showing here, and some not regularly arranged. But atoms get further away from each other when it gets hotter. So this is cold, and that's hot. Cold and hot. That's all there is to it. Now, you may wonder why, and what I'm going to tell you now, I'm not going to test you on, but I'll just tell that to satisfy your curiosity. I mean, why do atoms get further away from each other? The reason is that atoms don't sit still like they do on this image. They wiggle, they vibrate back and forth. And the amplitude of that vibration is what we call temperature. So these are cold atoms, these are hot atoms. Cold and hot. So as you vibrate over a bigger amplitude, you need more space. Right? Imagine your own atoms, you're not sitting like this, you're actually wiggling. As you wiggle over a big amplitude, you just need more space, and you push each other apart. Not just the 9 atoms that I've shown there. It's really all of them, the millions of billions of atoms that make up a solid. Cold and hot. Any questions? I knew I gave clear lectures, so thank you for reaffirming that. But you know, I'm not just going to hide this screen and then ask you, when metals get hotter, they expand because A, the atoms get closer together, B, they stay the same distance, C, they get further apart. That would be me delivering information to you, and you delivering that same information back to me. I'm going to see if you can take this idea of the atoms getting further apart when it gets hotter and apply it to a new context. So you better ask me questions. Cold and hot. I beg your pardon? What direction of expansion? In all directions. It's basically, it's literally like this figure here, but in 3 dimensions. So there are, of course, atoms in front and in the back. So the ones in the front come more towards you. The ones in the back goes towards the back. And if you put a constraint, let's say that they can't go to the back because there's something else there, the whole block moves forward. You know, in engineering, this is really important. Let's go back to this picture here. The picture in the background is that of a railroad that has buckled badly. You've probably been in a rail train at low speed, and you hear this clickety-clack sounds as the wheel goes over the little gaps between the different sections of the rail. You may wonder, why don't they just put the rail together? Well, if they did that, this is what happens when the rail expands. During the Olympics in London, what was it, last summer or the summer before? The summer before, they had to shut down the high-speed railway because for the high-speed railway, they have a different ways of putting rails together. It got very hot in London, and the rails were actually starting to buckle. If you, next time you park your car in a concrete parking structure, when you walk down, look down, you'll see that every 30 yards or something, there's a big gap filled with rubber. Why? Because concrete expands, and if you don't have that rubber, you know, you get a problem. And because the concrete expands lengthwise, height-wise, width-wise. Thank you for asking that question. Cold and hot. Last chance. Cold and hot. Yes?
What about liquids and gas?
But now we're going away from the question I'm going to ask. And liquids and gases is very different. You know, and there are some really weird things happening. For example, water, right? Water, you have your ice cube, which is colder than the glass of water. Float, which means it's less dense. So the atoms, or the molecules in their case, are farther away from each other. But we won't talk about any of that. We'll stay with solids. So if you're interested in, I'll give you a separate lecture on gases and liquids after my There was a hand up in the back there. It was the same question. Yes? Oh, very good. What dictates how much it expands? Different materials have what is called different expansion coefficients, and that has to do with the structure of the material and the type of atoms in there. But you can just look up tables, you know, copper expands by this fraction for a 1 degree temperature increase, and gold so much. And so different materials have different expansion coefficients, and that is determined by the arrangement of the atoms in the material and the properties of the atoms. I think you're ready for the question. So let me give you the instruction. I'm going to ask you the question, and then I'm going to give you a minute to think about this question. You're not allowed to talk to your neighbor. If I see you talk to your neighbor during that minute, I will come with one of those microphones, put it right in your face, and you'll have to tell everybody what you told your neighbor. Okay? So absolutely no talking. You vote. After that, when I tell you, you can talk to your neighbors. You must find a neighbor who has a different answer. So if your neighbor to your left gives you the same answer as you have, you say, thank you very much, and you turn to the right. If both of them have the same answer, you get up and walk around. If you've convinced that person, don't just go back to your seat and sit. No, find somebody else. It continues. Okay? If I ever see you sit like this without talking, I will come and talk to you. Okay? I tell that actually to my students too, and they don't like that, so they prefer to talk to their neighbors. So here we go. Wait a minute, 2 people have already responded? I haven't even asked the question. Okay, and remember, it's all of the atoms, right? Not just those 9. Consider a rectangular metal plate with a circular hole in it. Imagine we take that plate, we put it in the oven, heat it up. What is it that is going to happen to the diameter of the hole? Does the diameter of the hole increase? Does it stay the same? I haven't even finished reading the question. 23 people. Or does it decrease? Think before you answer. I'm going to give you 30 seconds. $15 more seconds. 1-5. Okay, we're at 2:15. Perfect. So go ahead, find a neighbor who has a different answer. So you got to check in with a few people, and then try to convince that person that you're right and he or she is wrong. Now look at that. Look at that. You all... That helped. You all got engaged. You all got fired up. I bet that by now many of you, look at them, they're still talking there. It's okay. I already said your salary doesn't depend on it. I bet that by now, most of you have forgotten that I'm not here to talk about metal plates with circular holes in it. I'm here to talk about education. The answer to this question really doesn't matter. I already made my point. Oh, look at that. It's wonderful to see how much attention I'm getting now. You know, and I bet that you're dying to get the answer to this question. But before I tell you the answer, imagine for a moment that I'd given my little lecture about thermal expansion. I mean, let's face it, what is more boring than metal plates with circular holes in it? And look at you now. Isn't it amazing how you can reawaken the curiosity of the human mind, right? Anyway, imagine that I'd given that little lecture, and then instead of asking you the question, I would have said, let's now apply this to rectangular metal plates with circular holes in it. If you take one of these plates and put it in the oven, turn up the temperature, the plate expands, and the diameter of the hole will I'm going to keep you in suspense a little bit longer here. I mean, you would have been sleeping through it, right? I mean, there's nothing more boring than that subject. So I think that one point that is a take-home message that is important is that teaching by questioning is very different from teaching by telling. Now, let's analyze for a moment what happened here. You thought about the question, and then you made a commitment. I made you make a commitment by pressing a button. And after you made that commitment, I asked you to externalize your answer. So you turned to a neighbor and you said, I chose because blah, 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 blah. And in the process, something really interesting happened. I could see it. I didn't even have to walk up to listen to you because all of you were gesticulating. You moved from the answer or the fact to the reasoning. It's the process that became important, not just, you know, a factoid or anything. It's the thinking that became important. But even more important, you became emotionally invested. If I were to tell you now, oh, gee, I'm sorry, I got to stop. I have to run to my next talk and walk out. You'd come running after me asking me what the answer to this question is. Even though this is a pretty boring subject. Okay, well, before we can get to the answer, you got to answer the question again. So please indicate what you now believe to be the right answer. Okay, we're about 200, 215, very good. Now, I have some bad news for you. I thought I gave a pretty darn clear lecture about thermal expansion. But only about 27% of you got the answer right the first time. So, and you know, the method doesn't work that well when it's 27. I mean, you have to have at least a third, 33%. So you were below that cutoff. There were many more people with the wrong answer than the right answer. And, you know, in a sense, you have made a very important point, which is actually one of the points I want to make during this lecture here. Because in essence, you've been telling me, Eric, your lecturing sucks. Which is exactly what I mean. Really, you should have done your reading before coming to this class, but those 2 paragraphs about thermal expansion. Okay, so let's see what we have now after discussion here. And actually a small miracle happened because the number of correct answers has increased significantly. You're still dying to know what the right answer is, right? The right answer is, I love the attention I'm getting now. I need a drum roll here. The right answer is number 1. And look at this. Look at this. The first distribution here in blue, you know, only 27% got it right. But the ones who were in the majority actually decreased. So even though you were in the minority, which, as I said, is because the question was a little bit too hard and because you didn't do your reading, it improved. I can see many of you still sit there thinking, you know, again, the question is not important, but I don't want you to lie in bed tonight at 2 a.m. thinking, you know, why does this whole increase? But so let me take another precious minute here. Imagine you have a jar of marmalade in the refrigerator. Glass jar, metal lid. The metal lid, you know, one of these bowl jars has a ring and a metal plate. You take it out, you try to open the jar, you can't. What do? You run the metal lid under hot water. The ring expands, the hole in the ring gets larger. You say, that's a ring. You asked about a plate. Okay, so let's imagine we have a metal plate. Here it is. No hole in it. Now we take a pen, a marker, and we draw a circle on this plate. And we put the plate in the oven. The plate will expand. And what happens to the diameter of the circle? It gets bigger. Everything gets bigger. You say, that's unfair. There's no hole. If there was a hole, then the atoms would expand into the hole, and it will get smaller, which is what most of you chose. Well, I'll tell you what's wrong with that reasoning. Imagine that we were to go outside. It's kind of chilly here, but we form a big circle holding hands. We are the atoms at the edge of the whole, all standing there, big, big circle. And now we all step inside towards the center of the whole. What just happened to the distance between us? It got smaller. Can't get smaller because our neighbor is shaking more. The only way to make the distance between us larger is to remove a few of us, but atoms don't disappear like that, or to make the whole larger. You won't forget this. Okay, back to peer instruction. I wish I could show you the data, but I have to wrap up. The first year that I implemented this, I doubled the learning gains. And over the years, by asking better questions in class, I tripled the learning gains. And people have shown similar gains across many, many disciplines, including better retention of material and better retention of students in STEM disciplines. I want to end by showing you two more small things that I think are really stunning and that reinforce some of the points I made initially. What is it that happens exactly in a lecture? Well, in a lecture, you know, it's very hard to pay utmost attention because you can't allow your mind to wander. You have to focus on taking the information down. I came across a paper from the MIT Media Lab, from the Effective Computing Group, where they're developing a sensor, a wrist sensor that you can, I have one, but I'm not wearing it right now, that you can wear around your wrist that measures electrodermal activity. This is as I said, the Effective Computing Group, and it basically measures neurological activity at the wrist. It also has an accelerometer so that it knows when you're moving your arm, and it can disentangle motor neuron activity from the sympathetic nervous system. And they show in this paper that you can correlate what you measure here with an EEG. You can't distinguish between alpha, beta, gamma, delta waves, but you can sort of get an overall idea of neurological activity in the brain. And they're mostly interested for doing pain monitoring and other things, but in this paper that I saw from 2010, which is completely focused on the electronics of the sensor and has nothing to do with education, there's one figure which shows data for an MIT student for a full week. In other words, they gave one of the MIT students the sensor and asked the student to just go about his or her business and then downloaded the data. You know, and it's much easier to do that with a wrist sensor than with EEG electrodes in your brain. I mean, you'd look kind of funny if you walked around like that. Maybe an MIT student would do that, but you know, most people would not like that. Let me show you that figure. Here it is. And as you can see, here is day 1, day 2, day 3, day 4, day 5, day 6, day 7 towards the top, starting on the far left here at 4 o'clock in the afternoon when the students started wearing the sensor, going all the way to 3 o'clock the next day. Then it took an hour to charge, and then and on. And as you can see, there are periods of intense neurological activity and some that are much less. They also asked the students to keep a little logbook of what he or she was doing. Those are the little letters underneath, which you can probably not read from where you are. I want to draw your attention to the parts of the trace labeled class. The trace goes flat. Compare that to sleep, which is this highlighted region here. Now, we all know that sleep is very important, right? Because memories get transferred from short-term memory to long-term memory. In other words, your students are more asleep in their lecture classes than they are in their own beds. Don't look at the screen, look at me, because then the answer to the next question is already on the screen. There is one activity, don't look at the screen, I said. There's one activity that matches class. What would that be? Watching TV. There it is. Watching TV. And this is something we've known for a long time. You put somebody in front of a TV, and they go into a meditative state. Why? Because there's the same thing happening. Information. There might be emotions, but there's no time to think. When you read a book, you can think. When you walk around, you can think. When you talk to somebody, you can pause and think. But when you're listening to a continuous stream of information, you can't think. I think that has huge repercussions for online learning and so on, because people watching video do not pause the video. In fact, most students who watch pre-recorded lectures online set the playback speed to 1.2 or 1.5 just to get to it faster. They don't take the time to pause and think. With a book, it's much more natural to do that. The other thing is you walk out thinking you know it. I have it all the time. I go to a colloquium. I used to organize the colloquium in applied physics, and you know, I wanted all my colleagues to come, but only half of them come. And you know, after colloquium, you walk through the hallway, and another colleague comes who has not been to the colloquium and says, "Did you go to that colloquium by this professor at Stanford?" I said, yeah. "How was it?" "Oh, it was," I want to make my colleague feel bad. "It was brilliant. It was really fantastic." "Really? What did he talk about?" And then you all of a sudden realize, yeah, it all sounded good, but you know, I can't really reproduce it. So it might have been inspirational, but I have not really learned deeply. Another experiment was done actually at Iowa State University, and I have to briefly turn to calico cats. Calico cats are the cats that have these fur patterns, and it turns out that in cats, the fur color or the fur pattern is encoded on the X chromosome. So 95% of calico cats tend to be female. So they took a biologist this study was done by the psychology department, it was done in the biology department. They asked a biologist to prepare a short lecture on calico cats, 10 minutes, and they recorded 2 videos with exactly the same content, same lecture, same content. In one, she looked right at the camera, stood up straight, and never referred to any notes. We'll call that the fluent video. In another one, she was slumped over her notes, reading haltingly, not looking confident or anything. But the content was exactly the same. So they recorded these 2 10-minute lectures. Then they took a large biology class, split it in 2. Half the students watched the fluent video, and the other half watched the disfluent video. Immediately after watching this video, they asked the students to predict how they would do on a test of the material. The students who had seen the fluent video predicted doing twice as well as the students who had seen the disfluent video. Then they distracted the students for about 10 minutes with irrelevant activities, and they tested the students. And you know what? There was no difference. In both cases, the information was transferred, but the learning had not taken place. And in part it is because you've not been confronted with any misconceptions. You have not had time to think it over and resolve any inconsistencies in your thinking. So you end up leaving a lecture with this false sense of security. You think you know it, but you really haven't even begun to learn. As an instructor, same false sense of security. You haven't gotten many questions. You must have given a great lecture. But in the end, it's just an illusion. It's just a house of cards. So, to wrap up here, education is not just about transferring information. It's not about getting students to do what we do. Interactivity is absolutely a must. And yes, we use clickers, but you could have done this without any clickers at all. It's not the clickers. It is the pedagogy that matters, not the technology. Thank you very much.